Okay, so let's go and look at the solution. You first suppose that the linear combination of the two vectors is equal to 0. Okay. Then you can write down then the augmented matrix of a linear system is 0, 0, minus 1, 1, 0, 4, 0, 0, 0. And formally, I mean, you could probably see the answer right, see what you're doing right away. We could do is row 1 with row 3. So we get to echelon form, minus 1, 4, 0. And then, well, even though, okay, then 0, 0, 0, and 0, 1, 0, and then we'll do one more. Row 2 swapped with row 3 to be the oh yeah, you don't want to drop. I mean, formally you could drop them, but you don't want to drop the 0 rows because that's just, we don't change the size of the matrices. Okay, so there's an echelon form, and your equations are, there's the A column and B column. So the second equation is B equals 0, right? This is back substitution. And then minus A plus 4B equals 0. But since B equals 0, this implies that A equals 0. Therefore, one solution, A equals B equals 0, and 0, 0, minus 1, and 1, 0, 4 are linearly independent. Okay? Questions? Are you guys, that's what you guys, I mean, more or less, not in terms of you're probably less expansive, but you can sort of see the flow. The thing you have to suppose, the augmented matrix, the equations that show that A, and then the conclusion that A equals B equals C equals 0, or A equals B. Okay. So let's do it says here problem 2 is now we're in P3, which is a polynomial vector space. So this is, it would be sort of to sort of see how it varies, is which of these subsets are linearly dependent and which are independent. So what I will do, I'll do B, and so the question here, so we have S equals minus x squared, 1 plus 4x squared. And so we want to know, so we do the same pattern. We suppose that the linear combination of the vectors equals 0, because that's the 0 vector, right? Now, we have to get the linear system, the augmented matrix. So and that's a little hidden here. So what we have to do is we have to write this out in terms of the terms of one order. So for example, we're going to have B times 1 plus 0 times X plus minus A plus 4B times X squared equals 0. Right? See, B is we're dividing up into terms, which are like a variable with one power, X to the 0 power, X to the 1 power, X squared. And so I've got, there's the 1, there's no X term. there's two terms, minus a and 4b for the x squared term. This is going to be the same polynomial. This is going to be the zero polynomial only when b equals 0. And let me start from this other, let me start from this one here. This top one here, this coefficient minus a plus 4b has to equal 0. Because this right-hand side is really 0 plus 0 times 1 plus 0 times x plus 0 times x squared. And the second equation is essentially b equals 0. Okay? And we could put a 0 equals 0 equation, but so we can leave it as this. So then, since this is a linear system, we can see that minus 1, 4, 0, 0, 1, 0, there's the augmented matrix. It's already in echelon form, right? The linear system's already in echelon form. So the idea here is you try to suppose the extra step. When you have column vectors, you can just read off the augmented matrix. Here, you have to go through the extra step and generate the equations or find the equations by doing a little algebra, right, to recombine these terms here. Then you find the equations. If you needed to, you could write down the augmented matrix, solve the linear system. Here we already know this is the A column and the B column. B equals 0 is the second equation. Then minus a plus 4b equals 0 is the first equation. Since b equals 0, that implies a equals 0. So a equals b equals 0. Therefore, linearly independent. Therefore, these are linearly independent vectors. Okay. Let's see. Let's try. Why don't you guys try? Although it's a little bit harder. Maybe well, it's probably. Let's try number. Let's see. Yeah, let's try C. S is equal to 2 plus x plus 7x squared, 3 minus x plus 2x squared, and 4 minus 3x squared. Is that set linearly independent? Okay, so it's 2 plus x plus 7x squared, 3 minus x plus 2x squared, and the third one is 4 minus 3x squared. So see if you can go through the process. Louise, do you have, you're done or you have a question? If you're, okay, yeah, it seems like your microphone isn't working if you're speaking. I assume that means, unless you put something in the chat, I assume that means you just are either working on your microphone or you're done. Oh, okay. I didn't see your, here, I didn't, now I see your chat message now that your microphone's not working, Remy, so you're all set. There, now I will not miss that. Okay. Well, shall I show you how to proceed? Okay. Well, you do the same thing you did before. You suppose that some number a times 2 plus x plus 7x squared plus b times 3 minus x plus 2x squared plus c times 4 minus 3x squared equals 0. That's your some linear combination. Then we want to solve this for a, b, and c. But the way we have to do is we have to divide it into coefficients of 1, coefficients of x, and coefficients of x squared. So there's some algebra to do. So we want to take the coefficients of 1, right? Well, that's going to be 2a from this term plus 3b from this term plus 4c from this term, okay? Then we have the coefficients of x, which are going to be a from this term. It's going to be minus b from that term and 0 from this term. You could say plus 0 times c if you wanted to. Then plus the coefficients of x squared, which are going to be 7a from this one, 2b from this one, and minus 3c from this one. Okay. Then for these to be the 0 polynomial, we would have to have let me see, I'm not sure if there's any, let's start from this one, 2a plus 3b plus 4c equals 0. That's this equals the 0. This one would be a minus b equals 0. That's this equation. And this one is going to be 7a plus. Looks like we're back. Zoom crashed. I guess you guys, I'm not sure if it crashed on your end, but it crashed on my end. Let's see. So let's. Okay, so Ramiz and Catherine, hopefully you guys are okay. And you heard that I don't know if if I crashed my client or whatever, but when we were back, I was reading off these equations, and I would have done 2a plus 3b plus 4c equals 0, and a minus b is 0, and then 7a plus 2b minus 3c equals 0. And there I have my linear system, so I can write down the augmented matrix of 2, 3, 4, 1, minus 1, 0, and 7, 2, minus 3, 0, 0, 0. And maybe the best thing is to swap row 1 and row 2, which I could have done by setting it up properly at the beginning. Minus 1, 0, 0, 2, 3, 4, 0, and 7, 2, minus 3, 0. I think that is okay. Then we can do minus 2 row 1 plus row 2 and minus 7 row 1 plus row 3 to give us 1 minus 1 0, and we do minus 2 plus that is 0, and minus 1 times minus 2 is 2 plus 3 is 5. And that doesn't change. And then we're down to the last, minus 7 plus 1 is 0, and minus 7 times minus 1 is 7 plus 2 is 9. And this doesn't change because it's a 0. Okay. If I make a mistake, tell me. Now, if we've got the X column clear, we have to clear the second column. Oh, the simplest thing is going to be maybe to do it in 2 steps. We've got a common factor here. We could do 1/3 row 3. Zero, 5, 4, 0, 3, minus 1. And then what do we want to do now? We could do, let's see, let's do it minus 3/5 row 2 plus row 3. 1 minus 1, 0, 0, 5, 4. And then this is going to, 5's cancel off, minus 3, and get 0 there. And this is the only, this is going to be, let's write it out, it's going to be minus 12/5. Minus 3 times 4 is minus 12/5 plus minus 1, which equals 5 over 5. So it's going to be minus 12 minus 5 is minus 17/5. Unless I've made some kind of mistake. But it doesn't really matter because this is in echelon form. And all variables are leading. So this is the A column, B column, C column. So from the last column, we have minus 17/5 C equals 0. So C equals 0. The second column is 5B plus 4C equals 0. But since C equals 0, that's going to lead to B equals 0. And the same thing, this is going to be, the last one is A minus B equals 0. But since B is 0, A is 0. Therefore, the 3 vectors are linearly independent. So, and you can see that this linear system didn't depend on the vectors being column vectors. You still got an augmented matrix, even though you were dealing with polynomial vectors. Okay. So you guys okay with that? We can go through, like, for example, here there's more of these, or you could go through, here's one with matrices. Are these 3 vectors linearly dependent? And, okay, let's see. Well, that's basically, there's some ideas in here that in this section, linear dependence, maybe, let's see. But this is basically what we need to do in linear independence and we can go and review and do more problems on Thursday. And then sort of see, because this provides this game, I guess you can also see other problems. For example, let's say that I had the question, so the question is this vector, is this vector, well, the question is, these ones here, I think, are linearly independent in S. We can check that, right? But I think these are linearly independent. Because if only two vectors, they're linearly independent if they're not multiples of one another. So you can't write either of these as a multiple of the other. So these are linearly independent. The question, so one of the problems we dealt with in the last section or first part of the chapter or the previous chapter was, is this vector in this set, in the span of this set? In other words, not this. Here's V, and the question was, is V inside the span of S? And this, so that if V is inside the span of S, then if I added V to S, I would have a linearly dependent set, right? But if it's linearly independent, then I could add it to this and I'd have a bigger set, a bigger span, right? So this question of is V in the span of S is relevant to trying to make a larger set of vectors. So, and you can see that when I do this, what I want to know is this vector in the span is related to another question, which is, can I show that some set of vectors spans a space? That's the other question here, which is like this. Does, for example, the question is, let's say we had this set. Let's go back. We had this set here, right? And we checked that it was linearly independent. But does it span? A separate question is, does this set span R3C? In other words, we checked it's linearly independent, but does it span this set here? Well, how would we check that? Well, we can check that it spans. Here's the problem. We did this before. We choose an arbitrary vector in R3, and we want to know whether it can be written as a linear combination of these things, which says A, 1, 1, 0, plus B, 1, 0, 1, plus Z, 1, 1, 1 would equal X, Y, and Z. Well, these were arbitrary vectors, right? You notice how similar this problem is to this expression is to the one that we started with in for linear independence. So if we solve this problem for these vectors, if this set spans this space, we could then use that solution to just set X equals 0, Y equals 0, and Z equals 0 to 0, and then check, does that force A, B, and C to be 0? So if we didn't know if this was linear independent, and we want to check both linear independence and whether it spans the space, you can check whether it spans the space, then use your solution to check linearly independence. So there's a pattern here. The question is, well, this is like solving an inhomogeneous problem with this same set of vectors, right? Linear independence involves a subset of this problem. It involves solving this for X, Y, and Z are 0. So does this set span the space would be the question of solving this linear system. Now, the same operations that brought this matrix to echelon form when these are 0 brings this one to echelon form, which was minus row 1 plus row 2, right? Which we give 0, minus 1, 1, but then here would be y minus x. This is a problem last time, but it's good to review. And then we have 0, 1, 1, z. And then we can do row 2 plus row 3 to give 1, 1, 0, x, y minus x, 0, minus 1, 1. Then we add these together and we get 0, 0, 2, and z plus y minus x, right? Because we add those two together. Then this is the A, the B, and the C column. Remember, we're solving for A, B, and C because we want to find, can I represent for arbitrary x, y, and z, can I find A, B, and C? So this is true. And then here I can see, well, the third equation is 2c equals z plus y minus x. So c equals 1/2 z plus y minus x. And this previous equation is minus b plus c equals y minus x. I want to solve for b, right? So b is going to equal, I pull it over here, I'm going to get c minus y plus x, because I leave the c here, add the b to this side, so I'm going to get, anyway, maybe it's better to multiply this by minus 1. There's the minus y minus x, and then bring the c over there. Okay, because then I have to put this in here, put the c in, so this is going to equal 1/2 z plus y minus x minus y plus x, which equals, well, let's look, there's going to be a minus 1/2 x and an x. That's 1/2 x. The y's are going to be 1/2 y minus y minus 1/2 y, because I've got 1/2 y, I'm going to have minus 1/2 y, and z is 1/2 z. So I found b, and you can see the last equation is a plus b equals x. So a equals x minus b, which equals x minus 1/2 x minus 1/2 y plus 1/2 z. So this equals x minus 1/2 x is 1/2 x. Let's see, x. Yes, I've done that. So this minus sign plus 1/2 y minus 1/2 z. So I have a solution for a solution for B, and a solution for C. So a bit of algebra. What it says is, you give me an x, y, and a z, any x, y, z you want, no restrictions, and I can tell you what A, B, and C are, so that this is true. Therefore, it spans the space. Okay? Because I can represent any vector I want in this span, so it spans the space. I've shown that any vector in the span is in the space. Any vector in the space is in the span.
Because there are three solutions.
Excuse me?
Because there are three solutions.
And you found a solution.
Okay.
The way it would fail is if this was 0 here, there'd be some constraint so that you could choose particular values of x, y, and z that would produce a contradiction. Now, but let's see. Well, let's say I didn't know whether those three vectors were linearly independent. So I can say, that test would be, suppose that A times 1, 1, 0 plus B times 1, 0, 1 plus C times 0, 1, 1 equals 0, 0, 0 for linearly independence. Then use previous solution with x equals y equals z equals 0 to see that a equals 0 from this equation, right? X, y, and z are 0. That b is 0 because x, y, and b equals 0, and c equals 0. So from this, you can see this one linear system, therefore, the three vectors are linearly independent. Okay? So
X equals Y equals Z equals 0, and because of
yeah,
that.
because if you notice that this solves it for any x, y, and z, but when we have to solve for linear independence is just the case when x, y, and z are 0. So if you had to both check this that it spans the space and whether it's linearly independent, you can check that it spans the space and then use that solution to find that they're linearly independent. So instead of solving the homogeneous problem and then doing the second one, that would be like solving it twice or something. Okay. Now here is, we're almost out of time. And let's see, have I been good? Okay. Here is sort of a preview that a set of vectors S that spans a space V. That means the span of S equals V, and is linearly independent is called a basis for V. Okay, so if you find a set that spans the space, it's big enough, right? Because any vector in V is in the span, but it can't get any smaller because because it's all linearly independent. If you took one of those vectors out, you'd be taking out a linearly independent vector, so you'd be losing vectors, so it would no longer span the space. So a basis is the smallest, is the right size set of vectors. Now, it isn't unique. There's lots of different bases for any space. So there's lots of different bases, but a basis is the right size it has no extra vectors. Right? It doesn't have any linearly independent vectors, but it still spans the space. So it's called a basis.
It's the right size for the.
It's a right size, it's the best. It's sort of like it sort of characterizes V, that you've got the most compact description. This gives a basis, gives the most compact and best, in some sense, description of a vector space. So, so we can go over this stuff because we're not, we don't. This is sort of the whole, the next 2 weeks, right? Is just linear independence and basis. You can see if you can understand linear independence and spanning the space, you've got what a basis is, because it's just a basis is just a set that spans a vector space. That is, the vector space can be written, any vector in the space can be written as a linear combination of these vectors, and it's linearly independent. It can't get any smaller. Now, it turns out this is the second result in the last 2 minutes today, is it turns out that the number of vectors in any basis for a vector space is always the same. So, for example, if you find a linearly independent set of vectors that spans a vector space, and there's 5 of them, any basis that you find is going to have 5 vectors. So the number 5 characterizes the space. Because if you have 3 vectors, it's going to, if you have a basis, you can't find, if you have a basis, if there's a basis for 3 vectors, you're never going to be able to find a basis with 3 or 4 vectors. With 2 or 4 vectors, if there's 3. So this number is called the dimension of the space. Because it characterizes the basis, but it's true for any basis, so it characterizes the space. Right? So the dimension is in short, the dimension of a vector space is just the number of vectors in any basis. Because every basis has the same number of vectors. So if you find it for one basis, you found it for them all. That's called the dimension of the vector space. So up above, we found that these 3 vectors, right? So here's a set. These 3 vectors, 1, 1, 0, 0, 1, 1, brother, 1, 0, 1, 1, 1, 1. Those 3 vectors span R3C and are linearly independent. So the dimension of RC3 equals 3, because that's the number of vectors in it. So this is what you think of. You think of this as naturally what you think of as 3-dimensional space is this number of vectors in the basis. But the point is that now you think of these as coordinate. These bases are sort of like in physics or engineering, you'd use them as coordinate systems, or they'd be they would be they would be sort of anyway. There are terms 1252. So this is what we're going to do. These concepts right here are everything we need sort of for the next 2 or 3 weeks, right? So it's good. So basically, you can spend some time to sort of like slowly go over things and review things, because these ideas are the crucial idea is a span and linear independence. Once you get those down, and if we practice them with different spaces, you've got everything. So I should let you go now.